When does quantum decoherence occur during quantum computation? Have you ever wondered how quantum computers maintain their unique abilities? One key factor is quantum decoherence, which can disrupt their performance. So, when does this phenomenon happen during quantum computation? Quantum decoherence occurs when qubits, the building blocks of quantum computers, interact with their surroundings. This interaction can lead to the loss of quantum coherence, which is essential for maintaining the special properties of qubits. When qubits lose their quantum states, they transition into classical states, which means the quantum information they hold is lost. Decoherence can start at any moment during quantum computation. If qubits are exposed to environmental noise or disturbances, such as thermal fluctuations or electromagnetic radiation, the risk increases. Material imperfections can also contribute to this issue. More specifically, decoherence begins when qubits lose their isolation. This happens when they start to entangle with uncontrolled external factors. As a result, the quantum phase relationships that allow quantum algorithms to work correctly are compromised. The time frame during which quantum computations can be performed accurately is known as coherence time. For many quantum systems, coherence time ranges from microseconds to milliseconds. This means that quantum algorithms must complete their tasks within this limited window to ensure reliable results. Throughout the quantum computation process, decoherence is a constant concern. However, it becomes particularly critical as computations grow longer or involve more qubits. The more qubits in a circuit, the greater the chances of decoherence occurring. Each additional qubit introduces more potential pathways for environmental interaction, making it a challenge to maintain coherence. Different quantum computing models experience decoherence in unique ways. In circuit-based quantum computing, decoherence typically affects qubits during gate operations and idle times. In contrast, adiabatic quantum computation or quantum annealing may see decoherence occur relative to the energy eigenbases of the system. Interestingly, some forms of decoherence in adiabatic quantum computing do not necessarily hinder successful computation, depending on how the system evolves and interacts with its environment. To combat decoherence, researchers use quantum error correction and fault-tolerant protocols. These methods requiring additional qubits and resources, but they are essential for improving reliability. Advances in qubit design, such as superconducting transmon qubits, aim to extend coherence times by minimizing noise and enhancing isolation. In essence, quantum decoherence happens during quantum computation whenever qubits interact with their environment in ways that disrupt their quantum coherence. This interaction limits effective computation time and accuracy. Managing decoherence is vital for the future of practical and scalable quantum computing.